So let us today understand how to calculate molar conductivity of weak electrolytes at zero concentration or infinite dilution. So many students have a lot of confusion with respect to this particular concept of zero concentration or infinite dilution, and then why can't we use the graph of molar conductivity versus square root of concentration to calculate the molar conductivity for weak electrolyte as well, when we can calculate for strong electrolyte. So let us understand some basic concepts before progressing with this. So first of all, as you all are already aware, what is electrolytic conductivity and what is molar conductivity? Let us see that. When I talk about electrolytic conductivity, that means I am talking about the conductivity which is happening in an electrolytic solution. So when we pass electric current through an electrolyte, so there will be electrical conductance per unit volume of the solution. So if I want to define what is electrolytic conductivity means electrical conductance per unit volume of the solution, as I have mentioned in point number 1. Okay. So what is molar conductivity? It is also an electrical conductance only, but it is an electrical conductance of 1 mole of an electrolyte in a given volume of a solution. So when we are looking at the electrolytic solution with respect to per unit volume or with respect to mole, the concept completely changes accordingly. So what happens is that in electrical conductivity, when we talk about electrolytic solution, if I dilute the solution, you know that on dilution what happens? On dilution, the number of ions will increase, because more you dilute the solution, more number of dissociation, the degree of dissociation increases, so the number of ions formed also increases, and hence when the number of ions are increasing, obviously the question will come to your mind that if the number of ions are increasing in an electrolytic solution, then the electrical conductance should also increase. Yes, but then what happens is that electrical conductance does not increase. Why? Because we are diluting the solution, and electrolytic conductivity is nothing but electrical conductance per unit volume of a solution. So with respect to volume of the solution, per unit volume, the number of ions decreases because we are diluting it. So the concentration is decreasing. So in electrolytic conductivity, with increase in dilution or decrease in concentration, the electrical conductance will decrease. Whereas in molar conductivity, the concept is completely different, because here if the number of ions are increasing, it will increase the molar conductivity. So molar conductivity is denoted by lambda naught. We know that very well. Now what happens when I plot the graph of molar conductivity versus concentration, square root of concentration, that is as per Kohlrausch. So, but before that, you need to understand that how do we calculate the molar conductivity of strong electrolyte and weak electrolyte, as well as you need to look at this particular graph which is of strong versus strong electrolyte and weak electrolyte. The graph is of molar conductivity, that is lambda to lambda naught, versus the square root of concentration. And Kohlrausch stated that basically the molar conductivity is a linear graph for strong electrolyte, whereas the molar conductivity versus square root of C is not a linear graph for the weak electrolyte. Now why is that? Very simple. If you look at strong electrolyte, the molar conductivity increases rapidly with dilution, and weak electrolyte also, the molar conductivity will increase rapidly with dilution. But molar conductivity, as you can see from the graph, varies linearly for strong electrolyte. So for in case of strong electrolyte, if I want to find out molar conductivity, I can just extrapolate this particular linear graph, isn't it? I can extrapolate this linear graph very well at whichever point I want to, and I can find out the respective molar conductivity. But if I need to find out the molar conductivity for a weak electrolyte, since this is not a linear graph, it is very difficult for me to find out at any given point what would be the molar conductivity of a weak electrolyte. As per Kohlrausch, what he stated, that molar conductivity is equal to lambda naught minus a square root of C, where your A is just a constant, C is the known concentration. That is what he stated. So molar conductivity of strong electrolyte very easily can be calculated using the graph by extrapolating the linear graph, whereas of weak electrolyte it cannot be calculated. I have mentioned all those points over here, that molar conductivity of strong electrolytes can be determined, whereas it cannot be used for weak electrolytes since lambda versus square root c is not linear. So how do we find out the molar conductivity for weak electrolytes at zero concentration or infinite dilution? That's our question now, right? So for this, Kohlrausch came with his law, which is a very simple law to understand. He stated that at infinite dilution. Now what do you mean by infinite dilution? Infinite dilution means that limitation of dilution after which there will be no effect on molar conductivity. That means the concentration has almost come to zero. That is why infinite dilution can also be called as zero concentration. So Kohlrausch stated that at infinite dilution, each ion migrates independently of co-ion and contributes to total molar conductivity. So I can state that lambda naught, that is the total molar conductivity of a weak electrolyte, is equal to n positive into lambda naught positive plus n negative into lambda naught negative. Why? Because I very clearly stated that as per this law, both cations and anions are independently contributing to total molar conductivity. So we need to find out how many moles of cations and anions are there, which are denoted by the symbol n positive and n negative. And then we need to know the molar conductivities of the respective cations and anions. Okay. And the product of number of cations, number of moles of cations and anions with the respective molar conductivities, the sum of both cations and anions molar conductivity will give you the total molar conductivity. This is what Kohlrausch stated. So I hope this particular part was very clear with respect to what is the law and how do we calculate the total molar conductivity. Now we will consider some example, and with the help of the example I'll try to explain you that how to calculate the molar conductivity of a weak electrolyte with the help of the molar conductivity of strong electrolytes. That means if you know the molar conductivities of strong electrolytes, say for example, if you've been given molar conductivities of HCl, NaCl and say sodium acetate, and they ask you to find out the molar conductivity of a weak electrolyte, so acetic acid. So we can do that. I'll show you in the next part of this. Just stay tuned to the end of this particular lecture so that you can understand Kohlrausch law very clearly and how to solve the numericals based on Kohlrausch law. So now let us understand Kohlrausch law application. Now you see total molar conductivity. When you need to find out total molar conductivity, how do you find out? You find out the molar conductivities of the respective cations and anions as both of them act independently. So number of moles of cations into molar conductivity of cations plus number of moles of anions into molar conductivity of anions, that will give you the total molar conductivity. Okay, now let me select a pen over here and we will go for an example. First of all, let us see how do I apply this particular formula when I need to find out lambda naught of KCl. Okay, I am trying to find out lambda naught of KCl. So I can write it as n positive of n of K positive, correct? So I can take over here n, that is number of moles of potassium ions, right, into molar conductivity, that is lambda naught at zero concentration of potassium ion, that is K positive, plus number of moles of chlorine ions into molar conductivity of chlorine ion. Now here I know that in KCl my number of moles of cation potassium is going to be 1 and number of moles of chlorine is also 1. So it is n K positive into lambda naught K positive plus n Cl negative into lambda naught Cl negative. Now let me consider one more example. So if we consider say lambda naught of barium hydroxide. Now barium hydroxide is BaOH twice, correct? So for this, how am I supposed to write down? This is going to be N of barium. Barium has a charge 2 positive and there is 1 mole of barium over here combining with 2 moles of hydroxide ion. So please pay attention. 1 mole of potassium combining with 1 mole of chlorine, or 1 mole of barium over here combining with 2 moles of hydroxide ion. So N of barium into lambda naught of barium 2 positive, correct, plus this is going to be 2 moles of hydroxide ion. So it is going to be 2 into N of OH negative ion into lambda naught of OH negative ion. So you need to consider the number of moles in order to calculate the total molar conductivity of a particular solution. That's how you do this particular solution. Now let us say example that I was actually considering to find out how to use the molar conductivities of strong electrolyte in order to find out the molar conductivity of weak electrolyte. So say for example you have strong electrolytes, molar conductivity, like it has been given to you that you know the molar conductivity of HCl, you know the molar conductivity of NaCl, you know the molar conductivity of CH3COONA as well, and you need to find lambda naught of say let us take acetic acid CH3COOH. This is the acetic acid whose lambda naught, that is the molar conductivity, you are supposed to find out. So how are we supposed to find out? Now in order to find out lambda naught of acetic acid, that is having CH3COO negative as the anion and H positive as the cation, correct? Now how do I combine all these strong electrolytes molar conductivity to give me the molar conductivity of CH3COOH? So it seems very simple that to find out lambda naught of CH3COOH, what I am going to do is here. So I'll be taking up lambda naught of HCl, right, plus say lambda naught of CH3COONA, right, and from here I'll subtract lambda naught of NaCl. You may ask me, why am I subtracting lambda naught of NaCl over here? It's very simple. I need CH3COOH, so I need the anion CH3COO and the cation H. But here NaCl is what I don't need, so I am subtracting the molar conductivity of NaCl, and all of them are like 1 mole of each of the ions, right? So if I break this particular expression, how am I going to break this expression? The expression gets broken up like this. So I would say, when we look closely, so it is going to be N positive, N of H positive, correct, into lambda naught of H positive plus N of Cl negative into lambda naught of Cl negative, that is for molar conductivity of HCl. The same way we'll be writing for molar conductivity of acetic acid, so that is lambda N of CH3 I'll just erase this, so we'll take it up as plus N of, this is CH3COONA, so here my Na is positive, so N of Na positive, that is number of moles of sodium ions, into molar conductivity of sodium ion, plus N of acetate ion, that is CH3COO negative, into molar conductivity of CH3COO negative, correct? Now coming to minus molar conductivities of Na and Cl, so N of Na positive into molar conductivity of Na positive, right, minus N of Cl negative into molar conductivity of Cl negative. And now here you can see this molar conductivity of Cl and Cl would get cancelled, molar conductivity of Na and Na would get cancelled, and you will be left out with only molar conductivity of hydrogen ion and here molar conductivity of acetate ion in this case, and that will give you together the lambda naught of H positive into N of H positive plus N of CH3COO negative into lambda naught of CH3COO negative. This will give you the total final molar conductivity of acetic acid. I hope this is very clear how to apply Kohlrausch law for finding out the molar conductivity of weak electrolyte. Thank you.